It's a crisp, clear night in 1997. The sky is a canvas of twinkling stars, each one a distant sun in its own right. Suddenly, something extraordinary happens. A cosmic traveler emerges from the depths of space, illuminating the heavens with a brilliance so intense it outshines even the brightest stars. This isn't the opening scene of a sci-fi blockbuster. This is reality. The arrival of Comet Hale-Bopp, one of the most breathtaking celestial spectacles of the 20th century. As it gracefully glides across the night sky, Hale-Bopp captivates millions of observers worldwide. Its dual tails, one of dust and one of ionized gas, stretch across the cosmos like cosmic brushstrokes, painting a picture of celestial beauty that would remain etched in the memories of all who witnessed it. For months, this celestial visitor dominates the night, visible even from light-polluted cities. It becomes a global phenomenon, sparking a renewed interest in astronomy and reminding us of the awe-inspiring wonders that exist beyond our planet. Hale-Bopp's appearance is more than just a visual treat. It's a cosmic wake-up call, prompting us to look up and marvel at the vastness and beauty of our universe. It reminds us that we are part of something much larger, a cosmic dance that has been ongoing for billions of years. Today, we're embarking on a fascinating journey to explore Comet Hale-Bopp in depth. This isn't just a story about a bright light in the sky. It's a tale of discovery, of pushing the boundaries of our knowledge, and of unraveling some of the mysteries of our solar system. We'll delve into why Hale-Bopp was so special. What made it outshine nearly every comet in living memory? How did its unprecedented brightness and longevity in our skies change the game for both professional astronomers and backyard stargazers alike? We'll uncover what we learned from its passage. Hale-Bopp wasn't just a pretty sight, it was a treasure trove of scientific data. Its visit allowed us to study comets in unprecedented detail, revealing complex chemical compositions and behaviors that challenged our existing models of these cosmic snowballs. But our exploration doesn't stop at what we learned then. We'll also examine how Hale-Bopp continues to influence our understanding of the solar system today. The comet's legacy lives on in current and future space missions, in the development of new observation techniques, and in our evolving theories about the early solar system and perhaps even the origins of life on Earth. This journey through space and time will take us from the outer reaches of our solar system to the labs and observatories here on Earth. We'll meet the amateur astronomers who first spotted this celestial wonder, the scientists who devoted years to studying it, and the new generation of researchers who continue to unlock its secrets. So, fasten your seatbelts and prepare for launch. We're about to embark on a cosmic adventure that spans billions of miles and billions of years, all centered around one extraordinary celestial visitor, Comet Hale-Bopp. If this cosmic journey has ignited your curiosity and left you starry-eyed, don't keep it to yourself. Spread the wonder of the universe by smashing that like button and subscribing to Exploring the Universe. By joining our community, you'll ensure you never miss out on our latest astronomical adventures. From comets to quasars, from exoplanets to dark matter, we're here to unravel the mysteries of the cosmos together. So, hit that subscribe button now, and let's continue our exploration of the greatest show in the universe. Remember, in the vast expanse of space, every like and subscription helps our channel shine a little brighter. Until our next cosmic rendezvous, keep looking up and stay curious. The story of Comet Hale-Bopp begins on a summer night that would forever change the landscape of amateur astronomy. On July 23, 1995, two men on opposite sides of the United States, unaware of each other's actions, made a discovery that would captivate the world. Alan Hale, an astronomer in New Mexico with a PhD in astronomy but working outside academia, was no stranger to comet hunting. He had spent over 400 hours searching for comets without success. On that fateful night, while observing known comets through his telescope, he spotted an unfamiliar fuzzy object near the globular cluster M70 in the constellation Sagittarius. Meanwhile, in Arizona, Thomas Bopp, a manager at a construction materials company and an amateur astronomer, was stargazing with friends in the desert. Using his friend's telescope to observe deep sky objects, Bopp also noticed the same unusual fuzzy patch near M70. Both men, following proper protocol, independently reported their observations to the Central Bureau for Astronomical Telegrams at the Harvard-Smithsonian Center for Astrophysics. The similarity and timing of their reports quickly confirmed that this was indeed a new discovery. What made this discovery truly extraordinary was the comet's distance from Earth at the time of its first sighting. When Hale and Bopp first observed it, Comet Hale-Bopp was an astounding 1 billion kilometers, about 7.2 astronomical units, away from Earth. To put this in perspective, it was beyond Jupiter's orbit. Most comets are only discovered when they're much closer to Earth, typically inside Mars' orbit. The fact that Hale-Bopp was visible from such an immense distance hinted at its exceptional size and brightness, promising an incredible show when it would eventually make its closest approach to Earth. This incredible distance of first sighting was unprecedented for comets discovered visually by amateur astronomers. It spoke volumes about the comet's size and reflectivity, immediately suggesting to astronomers that this could be an extraordinary celestial event in the making. The discovery also highlighted the crucial role that amateur astronomers play in the field. Despite the advanced technology available to professional astronomers, it was two amateurs who first spotted this comet, reinforcing the importance of backyard stargazers in expanding our knowledge of the universe. In the days following the discovery, astronomers around the world turned their attention to this new object. As more observations poured in, it became clear that this wasn't just any comet. Calculations of its orbit revealed that it would pass relatively close to Earth in 1997, promising a spectacular sight visible even to the naked eye. The discovery of Hale-Bopp also marked a turning point in how astronomical discoveries were communicated. While previous discoveries might have taken days or weeks to be widely known, news of Hale-Bopp spread rapidly thanks to the emerging internet, allowing amateur astronomers worldwide to quickly join in observing and tracking the comet. Comets are often described as dirty snowballs, but this simple analogy barely scratches the surface of these fascinating celestial objects. Let's delve deeper into the nature of comets. At their core, comets are primordial bodies composed of ice, dust, and rocky particles. The ice is not just frozen water, but also includes other volatile substances such as carbon dioxide, methane, and ammonia. This mixture is often referred to as the nucleus of the comet. A comet structure can be divided into several parts. Nucleus, the solid core of ice and dust, typically a few kilometers in diameter. Coma, a fuzzy atmosphere that forms around the nucleus as it approaches the sun tails. Streams of gas and dust that extend from the coma, sometimes stretching millions of kilometers. Most comets are believed to originate from two regions. The Kuiper Belt, a disc-shaped region beyond Neptune's orbit. The Oort cloud, a hypothetical spherical cloud of icy bodies at the outer edge of our solar system. Comets can be classified based on their orbital periods. Short-period comets, orbits of less than 200 years. Long-period comets, orbits of more than 200 years. The dirty snowball model. This model, proposed by Fred Whipple in 1950, revolutionized our understanding of comets. It suggests that the nucleus is a mixture of ices and dust, rather than just a cloud of gas as previously thought. As a comet approaches the sun, its surface begins to warm. This causes the ices to sublimate directly from solid to gas, bypassing the liquid phase. This process is crucial to the formation of the coma and tails. The sublimated gases and dust particles form a cloud around the nucleus called the coma. This can grow to be larger than most planets, sometimes reaching diameters of over 1 million kilometers. Comets typically develop two distinct tails. Dust tail, composed of tiny particles reflecting sunlight, often appearing curved and fuzzy. Ion tail, made of ionized gases pushed away from the comet by solar wind, appearing straight and bluish. Comet nuclei can range from a few hundred meters to tens of kilometers in diameter. For example, Hale-Bopp's nucleus was estimated to be about 60 kilometers across. While some comets may be smaller than 1 kilometer, spectroscopic analysis of comets has revealed a complex chemical makeup, including organic compounds. This has led to speculation about their potential role in delivering water and organic molecules to early Earth. Comets lose material each time they pass close to the Sun. Eventually, they may break apart due to gravitational forces or internal pressures, lose all their volatile materials and become inactive, resembling an asteroid. Be ejected from the solar system due to gravitational interactions with planets. While rare, comet impacts on Earth could potentially cause global catastrophes. This has led to increased interest in comet detection and tracking programs. The exceptional brightness of Comet Hale-Bopp was a result of several factors, with its size being the primary contributor. Let's delve deeper into the reasons behind its spectacular luminosity. The nucleus of Hale-Bopp was estimated to be about 37 miles in diameter. To put this into perspective, it's about 6 times larger than the famous Halley's Comet, which has a nucleus of about 10 kilometers. This size difference is akin to comparing a bowling ball to a basketball. The sheer volume of Hale-Bopp's nucleus provided an enormous reservoir of material that could be sublimated and ejected, contributing to its brightness. With its larger size comes a significantly greater surface area. As the comet approached the Sun, this expansive surface allowed for more ice to be exposed to solar radiation. The process of sublimation, where ice turns directly into gas, occurred across this vast area, releasing a tremendous amount of gas and dust into space. This ejected material formed the comet's coma and tails, which reflected sunlight and created the bright appearance we observe from Earth. Hale-Bopp's surface was found to be unusually active, with many areas of fresh ice exposed. This fresh, reflective ice contributed to a higher albedo than many other comets. The more reflective a comet's surface, the brighter it appears to observers on Earth. While Hale-Bopp didn't come as close to Earth as some other comets, its enormous size and high activity made it visible from great distances. At its closest approach to Earth on March 22, 1997, it was about 1.315 astronomical units away. Despite this distance, it was still exceptionally bright due to its size and activity. Most comets are only visible for a few weeks or months. Hale-Bopp, however, remained visible to the naked eye for a record 18 months, from May 1996 to December 1997. This prolonged period of visibility was due to its large size, which allowed it to sustain its activity over a much longer period than smaller comets. Hale-Bopp was producing an enormous amount of dust, estimated at 370 tons per second at its peak. This dust reflected sunlight efficiently, contributing significantly to the comet's brightness. Observations revealed that Hale-Bopp had multiple jets of material erupting from its surface, rather than just one primary jet as seen in many comets. These multiple active areas increased the amount of material being ejected and, consequently, the comet's brightness. The comet's chemical makeup also played a role in its brightness. Spectroscopic analysis revealed a complex chemistry, including organic compounds. Some of these compounds, when broken down by sunlight, may have contributed to the comet's luminosity. Due to its high activity and large size, Hale-Bopp developed an enormous coma, the fuzzy atmosphere surrounding the nucleus. At its largest, the coma was estimated to be about 2 million kilometers in diameter, larger than the Sun itself. This vast coma provided an immense surface area for reflecting sunlight. Hale-Bopp displayed two distinct tails, a dust tail and an ion tail. The dust tail, in particular, was exceptionally bright and well-defined, stretching over 100 million kilometers in length. This extensive, reflective tail significantly contributed to the comet's overall brightness. The orbit of Comet Hale-Bopp is a fascinating subject that provides insight into the dynamics of our solar system and the nature of long-period comets. Let's explore this in depth. Hale-Bopp's orbit is highly elliptical, which is typical for long-period comets. This elliptical shape means that the comet's distance from the Sun varies dramatically throughout its journey. At its closest approach to the Sun, it comes within about 0.914 astronomical units of our star, which is slightly closer than Earth's average distance from the Sun. At its farthest point, it travels out to approximately 370 Australian dollars, well beyond the orbit of Neptune and into the scattered disk region of the solar system. The comet takes approximately 2,533 years to complete one full orbit around the Sun. This incredibly long orbital period classifies Hale-Bopp as a long-period comet. To put this time span into perspective, the last time Hale-Bopp visited the inner solar system was around 2215 BCE. This was during the Bronze Age, predating the founding of Rome by nearly 1,500 years and coinciding with the construction of the Great Pyramid of Giza in Egypt. Hale-Bopp's orbit is inclined at an angle of about 89.4 degrees relative to the ecliptic plane. This near-perpendicular inclination is unusual and suggests that the comet may have originated from the Oort cloud, a theoretical sphere of icy bodies surrounding the outer reaches of our solar system. During its journey, Hale-Bopp's orbit is influenced by the gravitational pull of the Sun and the larger planets in our solar system, particularly Jupiter. These gravitational interactions can slightly alter the comet's trajectory over time, a phenomenon known as orbital perturbation. Due to its highly elliptical orbit, Hale-Bopp's speed varies dramatically. When it's far from the Sun, it moves very slowly. As it approaches the Sun, it accelerates due to the increasing gravitational pull. At perihelion, it reaches its maximum speed of about 28.3 miles per second. Hale-Bopp's orbital period of 2,533 years is relatively short compared to some other long-period comets. For instance, Comet West has an orbital period of roughly 250,000 years, and Comet Hyakutake takes about 70,000 years to complete one orbit. Based on current calculations, astronomers predict that Hale-Bopp will make its next perihelion passage around the year 4385 CE. However, due to potential gravitational influences from other celestial bodies, this date is subject to some uncertainty. The characteristics of Hale-Bopp's orbit provide clues about its origin. Its high inclination and long orbital period suggest that it likely originated in the Oort cloud. Over time, gravitational perturbations from passing stars or galactic tides may have altered its orbit, sending it into the inner solar system. The vast majority of Hale-Bopp's orbit takes it too far from Earth for observation. It was only visible to us for a relatively short period around its perihelion passage. This highlights the challenge astronomers face in studying long-period comets and emphasizes the importance of making the most of these rare close encounters. When we consider Hale-Bopp's 2,533-year orbital period, we gain a profound sense of the timescales involved in celestial mechanics. Since its last perihelion passage, human civilization has seen the rise and fall of numerous empires, the development of written language, and countless technological advancements. It serves as a cosmic timekeeper, marking epochs in human history. The passage of Comet Hale-Bopp through our inner solar system provided astronomers with an unprecedented opportunity to study a pristine celestial body. This study has had far-reaching implications for our understanding of the solar system and potentially for life itself. Let's explore these in detail. Hale-Bopp's composition offered a glimpse into the primordial materials present during the formation of our solar system. The comet's size and unusual activity suggested that the outer regions of the early solar system might have been more dynamic than previously thought. Studies of Hale-Bopp help refine models of planetary formation and the distribution of materials in the early solar nebula. The long period of visibility allowed for extensive observations, improving our understanding of cometary behavior and evolution. Hale-Bopp's size and brightness enabled the detection of rarer compounds, expanding our knowledge of cometary composition. The comet's activity far from the Sun challenged existing models of cometary behavior, leading to revised theories about coma and tail formation. The detection of complex organic molecules in Hale-Bopp's coma, including ethanol and glycolaldehyde, bolstered the hypothesis that comets could have delivered prebiotic compounds to early Earth. This finding supports the idea of panspermia, the theory that life or its precursors could be distributed throughout the universe by celestial bodies. It also suggests that the building blocks of life might be more common in the universe than previously thought. The study of Hale-Bopp spurred the development of new observational techniques and instruments. Improvements in spectroscopic analysis allowed for more detailed studies of cometary composition. The need for continuous observation led to advancements in automated telescope systems and image processing techniques. Hale-Bopp's visibility to the naked eye for an extended period rekindled public interest in astronomy. This led to increased funding and support for astronomical research and education programs. The comet's appearance inspired a new generation of amateur astronomers and future scientists. While Hale-Bopp posed no threat to Earth, its study improved our ability to detect and track large celestial objects. This has implications for identifying potentially hazardous objects that could impact Earth in the future. The comet study also enhanced our understanding of how such objects behave as they approach the inner solar system. Observations of Hale-Bopp's orbit and behavior help refine models of the outer solar system, including the theorized Oort cloud. This has implications for our understanding of how comets are distributed and how they might be perturbed into the inner solar system. The detection of various compounds in Hale-Bopp expanded our understanding of chemical processes in space. This has implications for understanding the chemical evolution of other celestial bodies, including planets and moons. The study of Hale-Bopp's composition provides a baseline for what we might expect to find in comets around other stars. This could help in the search for habitable exoplanets by providing clues about the distribution of water and organic compounds in other solar systems. Insights gained from Hale-Bopp have influenced the planning of future comet exploration missions. Understanding the composition and behavior of large comets is crucial for planning potential comet sample return missions. The study of Hale-Bopp brought together astronomers, chemists, biologists, and geologists, fostering interdisciplinary collaboration. This holistic approach to studying comets has implications for how we approach other complex scientific questions. Hale-Bopp's extended period of visibility demonstrated the value of long-term astronomical observations. This has implications for how observatories allocate telescope time and how astronomical studies are structured. Dr. Karen Meach, an astronomer from the Institute for Astronomy at the University of Hawaii, provided a pivotal perspective on Comet Hale-Bopp's significance. Her statement, "Hale-Bopp was a watershed moment in our understanding of comets. Its long stay in the night sky allowed us to study it with an unprecedented level of detail, revealing a chemical complexity we hadn't expected, encapsulates the revolutionary impact this comet had on the field of cometary science." Let's delve deeper into the implications of Dr. Meach's expert opinion. Dr. Meach's use of the term watershed moment underscores how Hale-Bopp marked a turning point in our understanding of comets. This comet challenged existing models and forced scientists to reconsider their assumptions about these celestial objects. The long stay in the night sky that Dr. Meach mentions was indeed exceptional. Hale-Bopp was visible to the naked eye for a record 18 months, compared to the typical few weeks or months for most comets. This extended period allowed for continuous monitoring of the comet's behavior, multiple opportunities to use various instruments and techniques, observation of the comet at different stages of its approach and departure from the Sun. The prolonged visibility of Hale-Bopp, combined with its exceptional brightness, allowed astronomers to use a wide array of ground-based and space-based instruments, conduct high-resolution spectroscopic analyses, observe subtle changes in the comet's activity over time, study the comet across multiple wavelengths, from radio to ultraviolet. Dr. Meach's mention of chemical complexity we hadn't expected is particularly significant. This revelation included detection of complex organic molecules, including some never before seen in comets, observation of rarer compounds due to the comet's high activity and brightness, insights into the chemical processes occurring within the comet's nucleus and coma. The unexpected chemical complexity of Hale-Bopp provided new insights into the composition of the early solar nebula, chemical processes in the outer regions of the forming solar system, potential sources of organic compounds on early Earth. The study of Hale-Bopp pushed the boundaries of existing technology and techniques, development of new spectroscopic methods, improvements in image processing and data analysis, advancements in coordinating global observation campaigns. The observations of Hale-Bopp led to revisions in models of cometary structure and behavior, new theories about coma formation and tail dynamics, improved understanding of how comets change as they approach the Sun. The complex chemistry observed in Hale-Bopp attracted interest from astrobiologists studying the potential for comets to deliver organic compounds to planets, chemists interested in molecular formation in extreme conditions, planetary scientists studying the role of comets in early planetary evolution. The insights gained from Hale-Bopp influenced the planning and design of subsequent comet missions, such as Rosetta mission to Comet 67P/Churyumov, Gerasimenko, proposed sample return missions to comets. Comet Hale-Bopp, one of the most spectacular comets observed in recent history, continues to fascinate both astronomers and the general public. Here are some intriguing facts and curiosities about this extraordinary celestial visitor. Hale-Bopp was visible to the naked eye for an unprecedented 18 months, from May 1996 to December 1997. This is in stark contrast to most comets, which are typically visible for only a few weeks or months. Its exceptional brightness allowed it to be seen even from light-polluted urban areas. Hale-Bopp displayed two distinct tails, a dust tail, composed of tiny particles reflecting sunlight, appearing yellowish-white, an ion tail, made of ionized gases, glowing with a blue tint. These tails pointed in slightly different directions due to their different interactions with solar radiation and the solar wind. The dust tail curved gently, while the ion tail appeared straighter. The nucleus of Hale-Bopp was estimated to be about 60 kilometers in diameter. This makes it roughly 3 times the size of the dinosaur-killing Chicxulub impactor. Its coma expanded to a diameter larger than the Sun at its peak. Spectroscopic analysis revealed the presence of previously undetected organic molecules in comets, including sodium and argon. The comet showed signs of containing significantly more carbon monoxide than water ice, unlike most known comets. Hale-Bopp began showing signs of activity when it was still beyond Jupiter's orbit, at about $7 from the Sun. This is highly unusual, as most comets only become active much closer to the Sun. The comet's appearance coincided with the tragic Heaven's Gate cult mass suicide in 1997. It inspired numerous works of art, music, and literature, becoming a cultural touchstone of the late 1990s. Hale-Bopp was independently discovered on July 23, 1995, by 2 amateur astronomers, Alan Hale in New Mexico and Thomas Bopp in Arizona. They spotted the comet on the same night, just minutes apart, leading to its hyphenated name. Hale-Bopp's orbit is highly inclined at 89.4 degrees to the ecliptic, meaning it travels almost perpendicular to the plane of the planets. Its orbital period is approximately 2,533 years, placing its previous perihelion passage around 2,215 BCE. Observations revealed a spiral structure in the comet's inner coma, suggesting complex interactions between the rotating nucleus and escaping gases. Multiple shells or halos were observed in the coma, indicating periodic outbursts of activity. Hale-Bopp was observed by more people than any other comet in history, including Halley's Comet in 1986. It was the subject of the most extensive observational campaign ever conducted for a comet. At its peak, Hale-Bopp reached a magnitude of -1, making it one of the brightest comets ever observed. It remained brighter than any stars in the sky for months. The comet's appearance coincided with the early days of the Internet, leading to unprecedented global sharing of amateur observations and images. It spurred advancements in digital astrophotography and image processing techniques. Some observers claimed to see a companion object traveling alongside Hale-Bopp, leading to various conspiracy theories. Professional astronomers debunked these claims, attributing the observations to background stars or imaging artifacts. Hale-Bopp is expected to return to the inner solar system around the year 4385 CE. Its orbit may be altered by gravitational interactions with other celestial bodies, potentially changing this date. The wealth of data gathered from Hale-Bopp led to significant revisions in cometary models and theories. It paved the way for future comet missions, influencing the design and objectives of spacecraft like Rosetta. The study of comets, particularly large, long-period comets like Hale-Bopp, continues to present both significant challenges and exciting opportunities for astronomers and planetary scientists. Let's explore the current state of cometary science and its future prospects. Predicting the appearance of new comets, especially those from the outer solar system, remains difficult. Challenges include the vast space to monitor, the faintness of comets when far from the Sun, the unpredictable nature of their orbits due to gravitational perturbations. Precisely calculating a comet's trajectory is crucial for predicting close approaches to Earth, planning observation campaigns, assessing potential impact risks. Challenges include accounting for non-gravitational forces like outgassing, which can alter a comet's path. Comets change over time due to solar heating and loss of volatile materials. Mapping this evolution process and predicting a comet's lifespan is complex. Determining the exact composition of cometary nuclei remains challenging due to the difficulty of direct sampling, the complex mix of materials in cometary comas, the changes comets undergo as they approach the Sun. Studying cometary interiors. Understanding the internal structure of comets is crucial but challenging without direct access. This knowledge is vital for models of comet formation and evolution. Maintaining consistent, long-term observation programs for comets is challenging due to limited telescope time and resources, the long orbital periods of many comets, advanced detection techniques. Implementation of wide-field survey telescopes like the Vera C. Rubin Observatory will greatly enhance our ability to detect comets earlier. Artificial intelligence and machine learning algorithms are being developed to automatically identify comets in vast amounts of observational data, predict cometary behavior based on early observations. Future space telescopes will provide unobstructed views of comets, free from atmospheric interference. These platforms could potentially detect smaller or more distant comets than ground-based telescopes. ESA's Comet Interceptor mission, planned for launch in 2029, aims to study a pristine comet or interstellar object. Future missions may include multiple flyby spacecraft to study a comet from different angles, landers designed to operate on cometary surfaces, sample return missions to bring cometary material back to Earth, development of miniaturized, highly sensitive instruments for future comet landers. These could perform real-time analysis of cometary material, including complex organic compounds. Advanced computational models will better simulate comet formation in the early solar system. Long-term cometary evolution. Interactions between comets and planetary bodies. Increased collaboration between astronomers, chemists, geologists, and astrobiologists to study comets holistically. This could lead to new insights into the role of comets in delivering water and organic compounds to early Earth. Concepts for spacecraft that could hibernate in the outer solar system and activate when a new comet is detected. Such missions could provide unprecedented long-term studies of cometary evolution. Development of more sensitive spectroscopic techniques to analyze cometary compositions from Earth. This could include the ability to detect more complex molecules and isotopic ratios. Improved understanding of comets will enhance our ability to assess and mitigate potential impact risks. This includes developing strategies for deflecting or disrupting potentially hazardous comets. Building on the observations of Oumuamua and Comet 2I/Borisov, Future studies will focus on detecting and characterizing more interstellar visitors. This could provide insights into the composition of other star systems. As exoplanet detection techniques improve, the study of comets and debris disks around other stars will advance. This could provide comparative data to better understand our own solar system's formation. Comet Hale-Bopp was far more than just a dazzling visual spectacle. It represented a significant milestone in our journey of cosmic exploration and understanding. This extraordinary celestial visitor left an indelible mark on both the scientific community and the public consciousness, teaching us invaluable lessons about the nature of comets and the history of our solar system. The sheer size of Hale-Bopp, with its nucleus estimated at about 60 kilometers in diameter, challenged our previous notions about comets. Its exceptional brightness, visible to the naked eye for an unprecedented 18 months, allowed for extensive observations and studies that were previously impossible. This extended period of visibility provided astronomers with a unique opportunity to conduct in-depth analyses, revealing complexities in cometary composition and behavior that we had never before observed. The chemical composition of Hale-Bopp proved to be far more intricate than anticipated. The detection of complex organic molecules in its coma and tail strengthened theories about comets potentially delivering the building blocks of life to early Earth. This finding has profound implications for our understanding of how life might have originated on our planet and the potential for life elsewhere in the universe. Hale-Bopp's visit also revolutionized our understanding of cometary dynamics. Its dual tail system, one of dust and one of ionized gas, provided new insights into how comets interact with solar radiation and the solar wind. These observations have helped refine our models of cometary behavior and improved our ability to predict the appearance and trajectories of future comets. Furthermore, the discovery of Hale-Bopp by two amateur astronomers underscored the continued importance of citizen scientists in astronomical research. It demonstrated that even in an age of advanced space telescopes and professional observatories, passionate individuals can still make groundbreaking discoveries. The legacy of Hale-Bopp extends beyond its time in our skies. It has influenced the design and objectives of subsequent comet-focused space missions, such as Rosetta and Deep Impact. These missions have built upon the knowledge gained from Hale-Bopp, diving deeper into the structure and composition of cometary nuclei. As we reflect on the impact of Hale-Bopp, we're left with a sense of anticipation. What cosmic secrets will the next great comet reveal? Will it challenge our current theories about the early solar system? Might it provide new clues about the origins of life? Or perhaps it will unveil aspects of cometary science that we haven't even considered yet. The story of Hale-Bopp reminds us that every celestial visitor has the potential to rewrite our understanding of the cosmos. It encourages us to remain vigilant, to keep our eyes on the skies, and to approach each new discovery with open minds and unbridled curiosity. I hope this journey through the fascinating world of Comet Hale-Bopp has expanded your horizons as much as it expands mine with every video. If you want to continue traveling through the cosmos with me, don't forget to subscribe to the Exploring the Universe channel and hit that bell icon to never miss a space adventure. Your engagement fuels our cosmic exploration, so please take a moment to like this video if you enjoyed it. It really helps our channel reach more curious minds like yours. Share this video with friends who also love the universe. Who knows? You might inspire the next great astronomer or astrophysicist. I'd love to hear from you in the comments. What aspect of comets do you want me to explore more deeply in future videos? Your questions and curiosity guide our journey through the stars. And remember, every like, comment, and share helps our channel shine a little brighter in the vast expanse of the internet. Before you go, here's a cosmic thought to ponder. Just as Hale-Bopp surprised us with its brilliance, the universe is full of wonders waiting to be discovered. Who knows? The next groundbreaking observation could come from your own backyard. Until our next video, keep looking up and remember, in the universe, curiosity is our fuel. This is Exploring the Universe, signing off until our next cosmic rendezvous. Ad Astra.